Well, today I am going to talk about thermonuclear runaways in degenerate matter. In degenerate matter. Right. So, I have thought of making this entire lecture in the following way. First, I will talk about the basics of this, and then I will talk about certain applications. Okay. Applications. Of course, in astrophysics. Right. And so, what are those applications? The first is helium flash. Then I'll talk about nova, and then I'll talk about X-ray burst. So this is the plan of my talk. Fine. Well, you see, to start with the basics, it is important to remember the difference between the equation of state for ideal gas, equation of state for ideal gas, and for degenerate gas. What happens in the case of ideal gas? Remember, pressure, it depends on temperature and density. So there is a dependence of pressure on density and temperature. Whereas for degenerate gas, the pressure depends only on density, not temperature. Now, you must be wondering why here the pressure is independent of temperature. So you must remember the fact that it is mainly because of the fact that this pressure derives primarily from the Pauli's exclusion principle. Right? And not thermal motion. That's why it doesn't depend on temperature. Okay, good. So, what you can see from here, the very important difference is that in an ideal gas, if I increase the temperature of the gas, the pressure will increase. Right? But in a degenerate gas, if I increase the temperature, the pressure will not increase. Right? So this is the most fundamental difference between the two of them. So in one case, if I increase the pressure, if I increase the temperature, the pressure increases. This is for the ideal gas. Right? Whereas the other case, the pressure remains unaffected or constant. And this is the degenerate gas. So this is the ideal gas, this is the degenerate gas. And this is the main reason behind the several very unique features, or you can say several very unique experimental observations of phenomena for degenerate gases. Okay, now let me talk about the thermonuclear runaway. Of course, we are talking about the case of degenerate gas. Right. Now, what are thermonuclear reactions? Do you remember? Thermonuclear reactions. You must remember that they are the reactions that happen in stars and are responsible for the creation of most of the elements that we see around us. Well, you see, when these thermonuclear reactions are triggered under degenerate conditions, then this lead to a violent energy release, because these thermonuclear reactions in degenerate gas actually assumes a positive feedback runaway. And as a result, a huge or violent violent energy is released. Okay. Now let me talk about the details. I'm not going to write all the finer details, but it is important to try to understand what is happening. Now I'm talking about here violent energy. Now what happens during thermonuclear reaction? Well, you do know that the ignition of reactions, right? So ignition of reactions, it releases a large amount of energy. That's true. Now, as a result of this large amount of energy release, the temperature increases, or you can say the local temperature T, it increases. Good. Now, if we have a normal gas, say ideal gas, then in such a case, what will happen is that this rise in temperature will cause an increase in pressure for an ideal gas. And what will happen as a result of increase in pressure? As a result, what will happen? The place where the temperature is high, this will expand, right? Due to increased pressure. And this expansion will this expansion of the region will cause this region to cool down. Right? It will cool down. The temperature will automatically drop down. And also, sir, very interesting thing, because of this expansion, the reason for this reaction was that the reactants were coming close to each other. Right? Now, because of this expansion of the region, the reactants will also now go far away from each other. And so, the reaction rate will also decrease. So, you see, if the increasing temperature causes the increasing pressure, then overall, because of the increase in the expansion of because of the increase in the volume, what happens is that we have a negative feedback here. Why negative feedback? Because initially temperature increased, then pressure increased, then it expanded, then what happens? The reactants separated and the region also cooled down. So the temperature decreased. So we have a negative feedback. However, in case of, just a second, yes, okay, but in the case of your degenerate matter, what happens is that even if the temperature increases due to the reactions, right? Even if the temperature increases, pressure remains constant. Okay. So, even if we have a sharp rise in temperature, the pressure remains constant. Now, what will happen? The thing that happens is that you must remember that these reactions mostly are charged particle reactions, right? And they have a very strong, they have a very strong temperature dependence, right? So, the increase in this temperature will cause a very rapid increase. So, if the pressure remains constant and they have a strong temperature dependence, so what will happen is that overall there will be a rapid rise in temperature, this rapid rise in temperature will basically cause rapid increase in reaction rate. Now what will happen? Increase in reaction rate means temperature increases even more. And so this means that again reaction rate will increase. So we have a positive feedback mechanism here. And as a result, the temperature keeps on increasing and the reaction rate keeps on increasing. Now as a result of this increased reaction rate, violent energy will be released. You understand? The reason for the violent energy released? And this is known as thermal runaway or thermonuclear runaway. Remember, this is basically a positive feedback mechanism. Okay. Now, another very interesting fact to remember is that because of the large thermal conductivity of degenerate matter, you see a thermonuclear runaway which is triggered locally, I mean in the entire region. If there is one place where we have a thermonuclear reaction, if this is triggered, then because of this large thermal conductivity, it will be what will happen? This will in fact spread to the entire region. It will be spread out in a very fast way. Okay, so a thermonuclear reaction which triggers locally under the degenerate conditions will spread rapidly through the rest of the degenerate matter. Okay. Now, you must be wondering, sir, is there a way that this feedback mechanism, this positive feedback mechanism will ever stop? Of course, nature has its way. You know what? What will happen? Let me tell you. What will happen? You see, this runaway, this will continue. Until what? Until there are enough electrons which are excited to states above the Fermi surface by the high temperature. And this will in fact lift the degeneracy of the degenerate electron gas. And then the equation of state will tend to be like that of an ideal gas. And the resulting increase in pressure with temperature moderates the reaction. See, so even if we have positive feedback mechanism, the excitation of electrons to level above the Fermi surface will later on cause the system to restore itself, or to moderate the reaction, and so ultimately from positive feedback it will go back to your negative feedback stable system. Now let me talk about the first application, which is the helium flash. Okay, so what is it? Now you see, when such a thermonuclear reaction occurs under degenerate conditions, so this helium flash is nothing but the thermonuclear runaway, again under degenerate conditions or degenerate gas, and this happens for the triple alpha reaction. then this is known as nothing but helium flash. And when does this happen? This happens during the red giant. You remember? When does helium flash happens? This happens during the red giant evolution of post main sequence evolution, initial phases. Now you see, this happens mainly for masses less than 2 solar masses, which ignite helium burning in the manner of helium flash. And what happens is that this result of the helium flash ignites the entire core of the star. So entire core entire core is ignited, okay, within seconds. This is important, within seconds. And that the temperature can, as a result of this, the temperature, it rises to more than 2 into say 10 to the power 18 Kelvin before this thermonuclear runaway begins to moderate. And do you understand how much energy is released within this time? Since the entire core is ignited, the total energy release is even more than 10 to the power 11 solar luminosity. It's a huge number, comparable to the luminosity of a galaxy. However, such extremely violent event we don't see normally. Why? We don't see the effects. The reason is simple. Because such a large energy release is almost entirely absorbed in expanding the envelope during the red giant phase. So we have a core and an envelope, right? And this entire energy, violently released energy, is absorbed by this envelope, which then moves apart, far away, expands. And that's why we don't see this energy released. Now, once the degeneracy of the core is lifted following the helium flash, or rather the more orderly initiation of the triple alpha reaction in heavier non-degenerate core, this core helium burning steadily approaches to carbon at a temperature of around 1.5 into 10 to the power 18 Kelvin. And this starts the horizontal branch phase of red giant evolution. Well, I have already talked about it in a separate video, so I am not going to talk about it here. Rather, I have talked about the very first application over here, which is the helium flash, right? Okay, now I am going to talk about the second application, which is nova. Now, what is a nova? Well, you see, some stars are observed to increase their optical brightness by as much as by a factor of 10 to the power 4 to 10 to the power 5. Right? In a matter of days. And then they slowly dim back over a period of months. And this is basically nova. Now, it is observed after so many investigations, simulations, it has been inferred that this nova, it is basically associated with binary systems where at least one star is a white dwarf, right? And there are certain observations. This is the first observation. Inference, you can say. The second is that the Doppler shifts indicate an expanding shell of gas emitting the light of the nova. Indicate expanding shell which emits the light of the nova. And the third very interesting thing, they can be recurrent such events. I mean, it doesn't just happen once, it can happen many times, several times. Okay, so these are the basic observations. Now, let's try to talk about what is a nova. Well, you see, a nova can occur in a binary star system, and here you see this is the white dwarf, this one, this is the white dwarf, and this is the companion star, right? Okay, and so you see what is happening here is that this star, companion star, it is basically a main sequence star, it can be a subgiant or even a giant star. And here we have the white dwarf. Good. So you see the matter from this star is being accreted slowly and in the white dwarf, and here we have the accretion disk. Here, this is the accretion disk. So this matter from the star accretes, and this accretion accretes in a thin layer on the surface of the white dwarf, because of the other star filling its Roche lobe and spilling matter over the white dwarf. Remember the concept of Roche lobe? So, if there is matter above the Roche lobe, then what will happen? That matter will be spilled over. It will lose the gravitational effect of this companion star, and it will be then getting gravitationally pulled towards this white dwarf. Okay, so this is what is happening. Matter from this first star is slowly accreted in a thin layer on the surface of the white dwarf, because of the other star filling its Roche lobe and spilling matter onto the white dwarf. And this happens typically through an accretion disk, or in fact also it can happen because of strong wind from the other star that the white dwarf captures onto the surface. Now what will happen is that eventually this layer ignites in a thermonuclear explosion under degenerate conditions, and the thermonuclear runaway blows a thin hot surface layer off into the surface, causing a large rise in light output from the system. Remember, everything is happening in a thin layer, right? And as a result, what happens is that resulting this thermonuclear runaway will blow away the thin hot surface layer off into the surface, causing a large rise in light output from the system, while the expanding shell outside the shell, it remains optically thick. Okay, see, here I have drawn it more in a better way. I think you will be able to understand, right? So this is the white dwarf, and it is slowly accreting the matter from the companion star over here, right? So this, if you look into the previous picture, so this is the stuff slowly. So here it is accreting matter from the companion star, and there is ignition of thin accreted surface layer here. This is the thin accreted surface layer, this one, and thermonuclear runaway happens until what? The degeneracy is lifted, and as a result what happens? You see, there is ejection of hot thin shell because of this ignition of the surface layer, there is ejection of the hot thin shell. You must also remember that basically this thermonuclear runaway is powered by nova, thermonuclear runaway. This is powered by hot CNO cycle. And this is a part of CNO cycle which happens at higher temperatures. And this is the one responsible for this. So this reaction is happening in the degenerate conditions over here. Now you must also remember that despite this large amount of energy release, a nova outburst typically ejects the matter ejected, this matter, right? This ejected matter, you see, this ejected matter is only about 10 to the power minus 4 that of the mass of white dwarf. So it's very small, right? And thus you see, as a result of this ejection, the white dwarf remains intact. It doesn't necessarily lose a large mass. There is not much mass loss over here, right? And this is confirmed by observation of recurrent nova. And how it can happen? Because it can again start. How? Remember, when the nova happened, nova was happening because of the companion star matter being accreted onto the surface of the white dwarf and then being ignited by hot CNO cycle reactions, right? Now, after this ignition, it can stop the accretion of matter. But again, after some time, the accretion of matter can start from the companion star because of some reasons, maybe the red giant evolution of this star. The matter from its Roche lobe will again be emitted outwards, and it will be again accreted in the white dwarf, and again as a result of this accretion it will again happen, the ejection. And this is the reason for the recurrent behavior of nova, because you see, the accretion can always happen eventually. And this, every time there is an accretion, there will be a nova explosion. Okay. Now let us talk about the third example, which is the X-ray burst. What is it? Now, all previous scenarios, remember what I talked about during the white dwarf, they all are applicable to this case. There is, however, only one difference, and that difference is over here. The other two are applicable. Only one difference is that, again, we have a binary system, and here one of the companion star, instead of white dwarf, this time it is a neutron star. Okay, and so you see, this X-ray burst is basically triggered by thermonuclear runaway under degenerate conditions, similar to that of a nova. However, you must remember the difference between white dwarf and a neutron star. The gravity of a neutron star is much more stronger than that of a white dwarf. And so what will happen is that here you see, yes, so what will happen, because of stronger gravity of neutron star, what will happen is that the falling matter on the surface of the neutron star, it will release more gravitational energy, and the thermonuclear runaway occurs at a much higher temperature and densities than that in the nova outburst, and as a result X-rays are produced rather than visible light in the explosion, and this is the reason for naming them X-ray burst. Now, talking about X-rays, I think you do understand how X-rays are emitted, right? Well, you see, X-rays are emitted when fast-moving electrons pass close to slow-moving ions and are accelerated. Now, in equilibrium, only if the temperatures are millions of degrees are the electrons moving at high enough velocities to produce X-rays. Well, the higher the temperature, the faster the electrons move, right? So, you see, this increases both the energy and the intensity of the X-rays. Why? Because collisions become more violent and more frequent at higher temperature. Another difference with that of white dwarf is that, you see, an X-ray burst on the surface of a neutron star, it may last for a few seconds, during which time the temperature can rise to, you see, the temperature can rise to as high as 10 to the power 9 Kelvin, and this causes the X-rays to be produced in abundance, very high temperature. Now what about nova? Well, for nova, most of them, the maximum temperatures is of the order of 10 to the power 8 Kelvin. So there lies another difference. So one is that of the neutron star, another is that of higher temperatures involved. Okay, good. Also, these higher temperatures, here X-rays are produced, and at lower temperature, in this case 10 to the power 8 Kelvin, this produces light at visible or other long wavelengths.